Give me just a minute, gentlemen. I'm taking attendance. Sorry for the late start. It's just computer was just really slow to warm up. Like it couldn't get it to behave properly until I started taking attendance. But it seems like it's okay for now. You know how technology could be. Hope everyone had a good weekend. We just got a lot of people in here. Yeah. If let me get everybody in here first before I make that announcement. Okay, I got one more. Okay. So let me think about it. I guess I need to update Bannerweb, but I calculated everybody's midterm grades. Let me make sure you guys can hear me. Testing. Okay. So this is the top of week 10, right? So week 12, we can expect exam 3 over chapter 2. It's only 3 sections. I calculated you all's midterm grade. I need to update Bannerweb, but your midterm grade is on Blackboard. If you know you've had like 4 or more unexcused absences, um, your name you should have received an email from me last week, seeing if you wanted to stay in the class. Um, yeah, if you know you've had like 5 or 6 unexcused absences or more, it's a good idea to probably just go ahead and send me an email anyway, saying, hey, I do intend to stay in the class, because like if you're on my list and I don't hear from you, like then because I'm gonna go through and submit names to be withdrawn for people that have like an excessive amount of unexcused absences. Otherwise, I can't think of any real announcements. We're just moving forward. Today we're going to be doing section 2.2. Let me hide everything else. And you know how it goes. Like if you have questions with anything, then just catch my attention, and we'll stop and talk about it. Let me just kind of set this up so I can at least monitor the chat. All right, looking good. Okay. All right, so probably what I'll do today, I'll go ahead and because 2.2 looks kind of like a long section, but I want like one clean stream of it. So what I'll probably do, once we hit that time for us to leave, I'll let you guys go, but I'll probably keep streaming until I reach the end. Let me see if this is, it looks okay. Okay, let's get the party started. So we're continuing with chapter 2. Chapter 2 is regarding polynomial and rational functions. Let me suppress the audio just so I can focus. And so section 2.2 is on polynomial functions. And so some objectives here. We'd like to learn properties of the graphs of polynomial functions. We want to determine the end behavior of polynomial functions, find the zeros of a polynomial function by factoring, identify the relationship between degrees, real zeros, and turning points, and graph polynomial functions. Let me check one other thing. Yeah, looks good. Okay. Okay. So we have some definitions. A polynomial function of degree n is a function of this form. So let's change that to like this. A function of this form, where n is a non-negative integer and the coefficients are real numbers where the leading coefficient is not 0, right? So let's start off by identifying what a monomial is. Like if you hear, I don't know if you ever heard the phrase like mono a mono, but a monomial is a polynomial degree of one term, right? So a monomial takes on the form where we have some x to some non-negative integer exponent, so x to some basically positive or non-negative counting number, and then a real coefficient. All right, so a monomial is just some variable to a non-negative integer exponent times some real number, right? So then a polynomial is just a finite sum of monomials. This is another monomial. These are all finite sums of monomial. Okay, again, a monomial is let me just do it like this. Let's go here. So some variable raised to some non-negative integer exponent times some real number leading coefficient, right? That's a monomial, right? Okay, and just stop me if anything isn't clear. Okay. More definitions. So the term an xn is called the leading term, right, of the polynomial. So it's the leading term. These subscripts, like this a sub n minus 1, it's just saying different real numbers, right? So it's just listing out the real numbers. And it's generalizing. We don't know which real number is any real number, right? So those coefficients are real numbers. And so the number a sub n is called the leading coefficient. So it's the number in front of the variable with the highest exponent. And then a sub 0 is the constant term. That's usually just a number, like no variables. A constant function f of x equals a, where a is not 0, can be written as a times x to the power of 0 is a polynomial of degree 0. So if you have f of x equal to a number, that's a constant function, we say that's a polynomial of degree 0 because we can write it like this. But if you have f of x equals 0, that's not necessarily a polynomial of degree 0. Yeah, right here. The 0 function, if we have f of x equal to 0, this has no degree assigned to it. Because, for instance, if we have f of x equal to 0, we can write that several ways. If we have f of x equal to 0, that's the same as, like, you can do, I don't know, 12.2 x to the power, let's do it like this, not 12.2. That's the same as 0 times x to the power of 3, which is the same as 0 times x to the power of 5. Notice how, so because the 0 function can be written in an infinite number of ways, that's why we say it has no degree, right? Which is also the same as like 0 times x to the power of 0, right? So on and so on. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials, respectively. So like this first one is called cubic, where the highest exponent is a power of 3, quartic, where the highest exponent is a power of 4, and quintic, where the highest exponent is a power of 5, right? Okay. So then this expression is a polynomial function defined by this. The function f, so this is a polynomial. The function f defined by this is a polynomial function. And then the last one is an example of a polynomial equation, right? It's kind of saying the same thing. Let me get this gentleman. Okay. So then the domain of a polynomial. In general, once you identify a function as a polynomial, in general, the domain is all reals, right? So that means if you were to look at the graph and domain is the very left to the very right, that means every x should be accounted for, right? So once you identify something as a polynomial, and remember, a polynomial is just a finite sum of monomials. And a monomial is basically a variable to some non-negative integer exponent times some real coefficient, right? Okay, let's try some more. So the graph of a polynomial function is a continuous curve, right? So, you know, there are no holes or gaps or breaks over here on the left, right? So that's indicative of a polynomial function. But on the right, notice we have a gap or a break, right? So if we try to trace it, in order to get to the next part, we have to pick our pencil up and then jump over that, all right, to get to the next part. So polynomials don't have like holes or gaps or breaks like this, all right? Okay. So one property of polynomials, again, is a smooth continuous curve or a continuous curve. And then this next part, the graph of polynomial functions is a smooth curve, right? So there are no, if you notice on the left, there are no sharp corners or edges or sharp turns or anything like that. But on the right, we have a sharp corner here, sharp corner. So when you have sharp edges like that in a graph, that's not indicative of a polynomial function. So main two properties of polynomial function of graphs, they have a smooth continuous curves. So no holes or gaps or breaks and no sharp corners or edges. If you have a hole or gap or break or a sharp corner or edge, then it's not the graph of a polynomial. Okay. So then with this example, we're asked to state which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. Okay. So notice, we have a finite, for part A, we have a finite sum of monomials, right? A monomial and a monomial, right? If we were to graph this graph would be like a W, right? The highest exponent is a power of 4, so generally it looks like a W. Part A is a polynomial. So then, if we're saying that A, we're going to say yes, polynomial. The degree of a polynomial is going to be the highest exponent. So then the degree of part A is going to be 4. The leading term is the term with the highest exponent. So then the leading term is going to be 5x to the 4. And the leading coefficient, I'm just going to try to squeeze it in here. Leading coefficient is going to be 5. Okay, just stop me. And again, stop me if anything isn't clear or if I need to go back or anything of that nature. I know. And then part B, now, this is a monomial, this is a monomial, this is a monomial. But remember, we said that the domain of a polynomial is all reals. But this one, we restricted the domain to 1 to 5. So this is not the example of a polynomial. So then B, we would say, is not a polynomial. All right. Okay. Let's see, how do we do? So we say that f of x is a polynomial for part A. The degree is 4. Did I talk about the degree? Yeah. The leading term is 5x to the 4, and the leading coefficient is 5. G of x is not a polynomial because the domain is not all reals. Okay. Moving along. So a function of this form is called a power function of degree n. Right. So we have f of x equal to essentially a monomial. Let me see, where a is a non-zero real number and n is a positive integer. Right, it's not the constant function. Right, yeah, okay, we're okay. So then let f of x be a power function. All right, let f of x be a power function. If the power is even, right, if the exponent is even, then if we were to consider negative x to the power of n with the even exponent, it's like the negative goes away. Right? So then f of negative x equals f of x. So then that's the definition. Again, that's the definition of a function being even, which means that we have y-axis symmetry. So whenever we say a function is even, that's the same as saying it has y-axis symmetry. That's the same as saying f of negative x equals f of x. Those three expressions can be used interchangeably. The graph is symmetric with respect to the y-axis, and the graph of x to the power n, where n is even, is similar to the graph of x squared. Right? Okay, so I think what we're saying so far is okay. Let's keep going. So then let f of x be a power function and say the exponent is odd. So then when we do negative x to the power of n, right, that's ultimately going to be negative, right? So if we have an odd number of negatives multiplied, the final result is negative. So then f of negative x is equal to negative of the original. So then that means we have origin symmetry. So that means one way we express it is whenever we have x comma y, we also have negative x comma negative y. All points are symmetric about the origin. So that means that they're like equidistant and mirror images centered around the origin. The graph of y equals x to the n where n is odd is similar to the graph of y equals x cubed. Okay, so this is like backstory, a lot of talk. I feel like once we start seeing some of these in action, this stuff will start to sink in. Initially, it definitely is information overload. Hopefully you all have been able to connect with the tutors. I guess you guys can hear me okay? Yeah. Hopefully you've been able to connect with the tutors. I know that one way to connect with the tutors is through Starfish. In the upper left-hand corner, that little hamburger symbol, the menu button, you click on that. At the bottom, you're going to see something that says Services. And then at the bottom of that list, you're going to see something that says Tutors. You definitely want to sit down with the tutors, work together, ask me questions. You definitely want to take advantage of these because that's what you pay for, right? You're not alone. You just got to take advantage of your resources, and it's totally okay. Just do what you need to do. The first thing is you gotta shake off the jitters. You have to abandon the fear, unless the fear is serving you, and allowing you to create the experience that you want. If it's not serving you, then it's a good idea to let it go. But if it is serving you and you're like super happy with everything, then keep it going. Okay. In behavior of a polynomial function, right? So the first case is where the leading coefficient is positive, right? Leading coefficient is positive. So then when the leading coefficient is positive, the graph is going to rise to the left and the right. The way I actually do it, when the leading coefficient is positive, that means it goes up to the right. All right? That's how I do it because there's a little bit more to it. So again, when the leading coefficient is positive, this to me it's more simple to say it just goes up to the right. The left-hand side is determined by the degree of the polynomial. We'll get back to that. But for right now, the leading coefficient is positive. That means it goes up to the right. If the degree of the polynomial is even, then the other side does the exact same thing. Again, let's do that one more time. When the leading coefficient is positive, the graph goes up to the right. When the degree of the polynomial is even, then the other side does the exact same thing. All right, let's see if that carries over into the next one. So that's the first case. Leading coefficient is positive, degree of the polynomial is even. Okay. Here, the leading coefficient is negative, right? So in the last one, we had a positive leading coefficient. It went up to the right. So now if we have a negative leading coefficient, what can we say? It should go what? Down to the right, right? So the leading coefficient tells us about the right-hand side. The degree of the polynomial tells us about the other side, right? So because the degree is even, the other side does the exact same thing. That's how I remember it. Negative leading coefficient, down to the right. Even degree polynomial, the other side does the exact same thing. Okay, let's try another one. Case 3, again, notice the leading coefficient is positive. So that means we should go up to the right. But now the degree of the polynomial is odd, so the other side does the opposite. Okay, and then let's just go ahead and touch on the last case and then do a quick recap. A negative leading coefficient, it goes down to the right. The degree of the polynomial is odd, the other side does the opposite, right? So what this is telling us, given a polynomial function, and this is just based off the leading term, right? This is in-graph behavior based on the leading term, or actually right now, this is based on the power function, but we'll extend it momentarily. But when the degree of the leading coefficient is positive, that means we go up to the right. Let's try that again. When the sign of the leading coefficient is positive, it goes up to the right. If the sign of the leading coefficient is negative, it goes down to the right. If the degree of the polynomial is even, the other side does the exact same thing. If the degree of the polynomial is odd, the other side does the opposite. That's how I remember. It's a little bit different nomenclature, but the same results as the way the notes are saying it. I just remember the sign of the leading coefficient tells me up or down to the right. The degree of the polynomial tells me what the other side is doing, right? So let's see if we can see, let's see this application of that. So given this polynomial of degree 3, we want to show that the power function, that this polynomial is approximately the same as the power function when the absolute value of x is very large, right? Okay, let's give this a go. So you wouldn't get, this is just for like context. You wouldn't really get this on your own. So let's see. So let's start with this polynomial. We have 2x cubed plus 5x squared minus, and this you can just watch. You don't really need to write anything. Also, I just want to say that, like, you know, all these things that you see me writing, I usually make a copy, a PDF version of all the stuff you see me writing. I make it available and I post it to our Blackboard page, right? So all of my students can access the same thing. Minus 7x plus 11, all right? So let me think about something. So now suppose we wanted to factor out, let me think about it. We can factor that out. We want to factor out, like, okay, I kind of, there's one little thing I'm thinking I'm missing. Give me a moment. Okay, so that's fine. So let's take this polynomial and factor out x cubed, right? So if we factor out x cubed, the following happens. Here's the x cubed. So now if we remove x cubed from the first term, we're left with the 2, right? If we remove x cubed from the second term, we're going to be left with 5 over x, right? Because if we distribute back, then the x will cancel and you get your x squared. The next term, we're going to be left with 7 divided by x squared. And the last term is going to be what? 11 divided by x cubed, right? So if we factor out x cubed, the following happens. Okay. So now, notice that, like, as x gets very large, right? If we focus on these terms here, as x goes off to positive infinity, and I want to say negative infinity as well, what happens here, right? What happens with these terms? Say for instance, we said 5 divided by 1 is what? 5, right? Say we said 5 divided by 2 is 2.5. 5 divided by 5 is what? 1. So notice that as this denominator gets bigger and bigger and bigger, what happens to this term? This term gets closer and closer and closer to some number. All of these terms get closer and closer and closer to some number. What do you think happens? Say we said 5 divided by 100. Is that a really large number or a really small number? Say we said 5 divided by 1,000, 10,000, a million, right? So as x goes way to the right, these terms get closer and closer and closer to 0. They all get closer and closer and closer to 0. Right? As x gets very large. Let me see. I feel like there's something else. So then, as x gets large, these terms go to 0, and that leaves us with, I'm going to say right now, that's approximately 2x cubed, right? Let me see. There's something that I'm missing there though. So here's the type version. We factor out the x cubed. We got this part, right? So then when the absolute value of x is very large, so that's the only other thing, right? When absolute value of x is very large, then those terms essentially go to 0, and we finish with our desired result, right? So that's it. So that's the only thing I was missing, that when absolute value of x is very large. But the idea still holds. It's essentially the same. Okay? And I want to say something similar can be shown for the other end, when x goes to negative infinity as well. It's a similar thing. Okay? So what that's showing us is that, what this is showing us is that as x either gets very, very large or very, very small, this polynomial behaves in a similar fashion to this power function, right? And we just saw those rules for the power function where if the leading coefficient is positive, it goes up to the right. If the leading coefficient is negative, it goes down to the right. If the degree of the polynomial is even, the other side does the exact same thing. If the degree of the polynomial is odd, the other side does the opposite, right? So we just explored those properties of the power function, but because this polynomial, as x gets very, very large or very, very small, it behaves similar. So then that means that we can extend those characteristics for the power function to the polynomial functions, right? So then now we have the official leading term test. So given a polynomial, given this polynomial function and the leading term is some an x to the n, basically a power function, then the behavior of the graph as x goes to positive infinity or negative infinity is similar to the same. It basically has the same properties as the power function. All right, that's all that we're saying. So for instance, given a polynomial, say the leading coefficient is positive. Notice the graph is going up to the right. This slide is actually missing something. It should also say that the degree of the polynomial is even. So we'll say the degree is even. Right, that's what it's missing. Even means the other side does the exact same thing. Yeah, I think all of these are missing the degree. So when the leading coefficient is negative, notice it's going down to the right, and this is still even. The degree of the polynomial is even. Okay, it's definitely missing that. I didn't see that until now. Case 3, notice the leading coefficient is positive, so it's going up to the right, and in this case, the degree of the polynomial is odd. All right, that doesn't mean the function is odd. We're just saying that the highest exponent is odd. So that means the other side does the opposite. And the last one is also the degree is odd. Okay. So notice the leading coefficient is negative. It goes down to the right. And then with the odd degree polynomial, the other side does the opposite. Okay. So that's the leading term test. I feel like there should be questions. I'm hoping you guys are still there. We got official like about 6 more minutes in class. I'm going to keep going. Let's at least maximize the 6 minutes, and then after 6 minutes, I'll let you go. So if you need to keep it moving, but let's see this in action. I feel like this will be a lot easier to see in action. So it says use the leading term test to determine the end behavior of the graph. So if we were to graph this using the leading term test, so first notice that the leading, first of all, what is the leading term, right? The leading term is the term with the highest exponent. So in this case, the leading term is this guy, right? Because the highest exponent is 3. So notice that the leading coefficient is negative. So because the leading coefficient is negative, it should go down to the right. And then the degree of the polynomial is odd, which is at 3. So then that means the other side does the opposite. So it should go up to the left. It should go down to the right, up to the left. So if we were to look at this graph, like in the far right, it should be going down, and the far left should be going up. Okay. So here, the degree of the polynomial is odd, and the leading coefficient is negative. So we're talking about case 4. I feel like that's not a proper symbol either. I think that's supposed to be an arrow. But basically, we said it falls to the right and rises to the left, right? So you can see it. You can see where it matches right here. That one and this one, right? I think these are supposed to be arrows. I think these are like typos. I think so, because that symbol doesn't make any sense. But if it was like y goes to infinity as x goes to negative infinity, I think those are supposed to be arrows. So let me do this. I think that's supposed to be an arrow, 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 arrow. I think that's what that is. Because like this is basically saying y goes to positive infinity as x. So as it goes to the far left, y goes up. As we go off to the far right, y goes down. All right. Let's try another one. We got 5 minutes. Okay, so that was an intro to the leading term test. And again, once you start working examples, I think it'll sink in. But again, the way I remember, if the leading coefficient is positive, it goes up to the right. If the leading coefficient is negative, it goes down to the right. If the degree of the polynomial is even, the other side does the exact same thing. If the degree of the polynomial is odd, the other side does the opposite. Right? So even means exact same, odd means opposite. So then next we want to introduce this concept of real zeros of a polynomial function. So if f is a polynomial function and c is a real number, then the following statements are equivalent. So the following statements we can use interchangeably. The first is that say c is a zero of f, but that's the same as c is a solution or root of the equation f of x equals 0. I think he's in the next class. No, he's in this one. He got lucky. Man, you guys be getting lucky that I be in a good mood. I give y'all attendance credit. Like I shouldn't give it to him, but it's okay. We have bigger fish to fry than worry about attendance. Just be here though. You don't want to not try to get your credit. C is an x-intercept. Okay, so C is a zero of the function. C is a solution or root of f of x equal to 0. And C is an x-intercept of the graph of f. All these statements can be used interchangeably. So whenever we say find the solution or find the 0 or find the x-intercept, we're saying the same thing, just 3 different ways. Okay. So find all the zeros of each polynomial function. Let me think about it. So basically saying find the x-intercept, right? So if we want to find the x-intercept, can we set y to 0 and solve? Okay, we're going to try these out. I feel like I might need some more space, so I'm going to give myself some space. Let me get a copy of these. I don't need both of them. Let's take it from here. Give me just a moment, getting a copy. Shoot. Add a page. Cool. All right. I'm watching the clock. Let's go like that, and let's go paper. Let's do some lines. Okay. So we want to find the zeros, right? So for part A, basically find the x-intercepts. So for part A, we have f of x equals x to the 4 minus 2x cubed minus 3x squared, right? If we want to find the x-intercept, we set y equal to 0 and solve. Now, off the rip, notice that there's a greatest common factor, right? So hopefully with the lab, you guys have been getting some practice on factoring. You are expected to be comfortable with factoring for this course. That's what the lab is for, to kind of fill in those things that you're supposed to already know coming into the course. Let me try to wrap this up because we got about a solid 2 minutes. So there's a greatest common factor, right? We can factor out x squared from every term. So if we factor out x squared, what are we going to be left with? All right, the first term is x squared minus what? 2x minus 3, right? Can we factor that into something of this form where we have x and x, one's going to be plus and one's going to be minus? Is it a negative 3 and a positive 1? We're looking for two numbers that multiply to give us negative 3 and add to give us negative 2. Notice that 1 times negative 3 is negative 3, and then 1 plus negative 3 is negative 2, right? And again, this is still equal to 0. So now, zero factor property, we have things that multiply to give us 0. So then, long story short, either x equals 0, or what, x equals negative 1, or x equals 3, right? So I want to say those are the solutions there. Let me try the other one with the time we have remaining. We'll check it, and then I'll let you go. But I'm probably going to keep streaming until I finish. Just give me a couple more minutes. And then part B. So I'm going to go with that. And then part B, we have this g of x equal to, we have x cubed minus 2x squared plus x minus 2, right? So if we want to find the zeros, again, we need to set this equal to 0. There's no greatest common factor, but I'm going to try a technique. Whenever you have 4 or more terms, I'm a fan of trying a technique called factor by grouping, right? So for instance, if I group the first 2 terms together, right? What do they have in common? Well, from the first 2 terms, we can factor out x squared. We're going to be left with x minus 2. The hint is we are looking for x minus 2 on the right, which we, by the good grace of God, we already have. Don't forget that plus right there, right? So now in this form, now we were able to get it. This is called a common binomial factor, right? So after we group them into groups of 2, so now the left term and the right term separated by that plus, they have something in common, right? What color do they have in common, or what item do they have in common? They both have that blue thing, right? So we can actually factor out that's called the common binomial factor. We can factor that out from each term, right? So if we factor out the blue thing from both sides, okay, we're going to be left with, on the left, we're left with x squared. On the right, we're left with the plus 1, right? That's a little bit, I know that gives people a hard time, right, to get that factor. So that's something that will come out during the lab, hopefully, okay? So now that we factored it, we don't have a sum of cubes, so this can't be factored any further. But this x minus 2, hopefully I'm not missing anything. We're going to check it momentarily. So then on the left where we have the x minus 2, that tells us that x equals 2. That's the only 0 that we have. Okay, let's see how do we do if we got everything. Go paper. Okay. So we got 0, -1, and 3, and then we only got 2 from part B. Let me check this real quick and I'll let you go. 0, -1, and 3 from part A, and then 2. So you see that they did exactly the same thing. All right? Okay. So with that, I don't want to keep you guys any further. I'm going to keep streaming. But you're welcome to go. And you know, the remainder of the stream will be up on my channel. Again, you guys should be subscribed with your notifications turned on, so whenever I do go live, you know. Once you get out of my class, you can at least, you know, you can leave the subscription just as an homage or as gratitude, but you can turn off like your notifications, but just leave the subscription. But I mean, at least while you're in my class, use it because that's how I communicate with you guys. Okay, guys. So yeah, this is the top of week 10. Week 12, you can anticipate exam 3 over chapter 2, sections 2.1, 2.2, and 2.3. Right now, we're working on section 2.2, and then we'll be working on assignments on Wednesday. Okay, enjoy the rest of your day, guys. I'll see you on Wednesday. I'm going to keep going, though. Okay, so this next concept we have is the intermediate value theorem. Let a and b be two numbers such that a is less than b. If f is a polynomial function such that f of a and f of b have opposite signs, then there's at least one number c where c is between a and b for which f of c equals 0, right? So a and b are two numbers such that a is less than b, and we're given a polynomial function. So remember, one of the properties of polynomial functions that we discussed earlier is that it's a continuous graph, which means there are no holes or gaps or breaks, and it's a smooth curve, so there's no sharp corners, edges, or anything of that nature. So then we have a is less than b, and then when we evaluate f of a and f of b, they have opposite signs. Because polynomial functions are continuous, that means that at some point, if the y value goes from positive to negative or vice versa, at some point we have to cross the x-axis, right, in order for y to go from positive to negative. So then that's the intermediate volume theorem. So as long as c is between a and b, and we're working with a polynomial function, and then f of a and f of b have opposite signs, then there has to be some c between a and b where basically it's going to be the x-intercept, right? So for instance, right, given a polynomial function, so notice here f of a is positive, f of b is negative, so there has to be some c between a and b right here where it crosses the x-axis. F of a is negative, f of b is positive, some c between a and b where it crosses the x-axis. That's the intermediate volume theorem. Okay, let's keep going. And then you can also have, you're guaranteed at least one with those conditions, but you could have more than one. Okay. So show that this function has a real 0 between 1 and 2, right? So first we identify it as a polynomial. Notice that each term is a monomial. We have a finite sum of monomials. You can say that the domain is all reals, okay? So we've identified this as a polynomial function. So then if we want to show that it has a 0 between 1 and 2, all we need to do is evaluate when x is 1 and when x is 2. So if we look at f of 1, that's going to be negative 2 times 1 cubed plus 4 times 1 plus 5. So that's going to be a negative 2 plus 4 plus 5, 7. Okay, so notice that's positive. Okay. Then if we evaluate f of 2, negative 2 times 2 cubed plus 4 times 2 plus 5. 8 times 2 is what? Negative 16 plus 8 plus 5. That's going to be negative 8 plus 5 is negative 3. Notice that this one is negative. All right? So then, I mean, that's all that we really needed to show, is that one of them gave us a positive result and the other gave a negative result. So then that means that there has to exist a 0, some c between 1 and 2. That's basically the x-intercept, right? So we get a positive result, a negative result. So because they have opposite signs, and by the intermediate volume theorem, there has to be a 0 between 1 and 2. Okay. Moving along. All right. A polynomial function of degree n. So let me see. Now we want to look at real zeros of polynomial functions. So a polynomial function of degree n with real coefficients has at most n real zeros. Okay. So for instance, that's like if you had a squared function, you're not going to have 3 real zeros. You have at most 2. You could either have 2 real zeros or 1 real zero or no real zero, right? So find the number of distinct real zeros of the following. It says find the number of distinct real zeros of the following polynomial function of degree 3, right? Okay, so we're fortunate with part A because it's already factored for us, right? So if we wanted the zeros, if we set this equal to 0 and solve, we would get what? So for part A, we get what? X equals 1, x equals -2, and x equals 3, right? So it's 3 distinct real zeros. See, like this is one thing. This is a qualm that I have with the English language. How come, like with heroes, the word heroes is OES, but zeros is just OS, right? That always irked me. That's one of the reasons why I decided to study math over literature, because literature is like you have to have some experience with each thing. You can't like figure it out on the spot, because if you haven't seen it before, based on whatever rules, I just didn't like that. And anyway, I have nightmares about literature, which I get. We speak it, I get it, but I don't resonate with it. Anyway, so we got 3 distinct zeros. Okay. Let's see. So for part B, for instance, if we set each thing equal to 0, that second term, the x squared plus 1, there's no real zeros there, but then the first one, we get 1, right? So for part B, what, x equals -1, so 1 real zero. Okay. Okay, and then C, we're fortunate because these are already, so let me see. We have what, x equals 3 and -1. It's 2 distinct real zeros. The first 0 has a multiplicity of 2, but we're not gonna use that just yet. So, but distinct real zeros, we get what, x equals 3 and x equals -1. Just doing the same thing. So 2 distinct. Okay. Okay. Let's okay. So f of x has 3 real zeros, okay? Has 1 real zero, has 2 distinct real zeros, okay? Let's keep it going. We're not too far off. I guess I don't have to do too much more. Okay, so multiplicity of a 0. So if c is a 0 of a polynomial function and the corresponding factor occurs exactly m times when f of x is factored, then c is called a 0 of multiplicity m. So if m is odd, the graph of f crosses the x-axis at that 0. If m is even, the graph of f touches but does not cross the x-axis at that 0. All right? So let's see this in action. So if the multiplicity is odd, it's going to cross at that 0. If the multiplicity is even, it's going to bounce off the x-axis. It's going to touch but not cross. Okay. So find the zeros of the polynomial function and then give the multiplicity of each 0, right? So again, we're fortunate because this is already factored for us. So if you set it equal to 0, basically you set each thing equal to 0 and solve, we'll get a result of x equals 0, x equals -1, and x equals 2, right? The first one, where you have the x squared, that has a multiplicity of 2. So that has an even multiplicity. So it's Yeah, multiplicity of 2. These other ones, the multiplicity is 1 because the exponent is 1. Okay? So what that means is that when x is 0, the graph is going to bounce off the x-axis. When at these other x-intercepts, the graph is going to cross the x-axis. Right? So it looks like we have a degree 4 with a positive leading coefficient. So then you would probably expect like a W where it's like decreasing, it crosses at -1, it bounces at 0, and then it crosses back at 2, right? So we'll get into some of those notions. So the 0 has a multiplicity of 2, while each, the -1 and 2 have a multiplicity of 1. Okay. So then turning points. A local or relative maximum value of f is higher than any nearby point on the graph. That's a maximum, right? So when it's like basically the top of a mountain, the peak of a mountain. And then a relative minimum is a value of f that is lower than any nearby point on the graph. So that's like the bottom of a valley. The graph points corresponding to the local max and local min are called turning points. At each turning point, the graph changes from increasing to decreasing or vice versa. So for instance, we have a maximum value of 12 when x is -1. We have a minimum value of -15 when x is 2. Okay. So if f of x is a polynomial of degree n, then the graph of f has at most n minus 1 turning points, right? So whatever your degree of your polynomial is, you have at most n minus 1 turning points, right? All right, so using a graphing calculator and this window to find the number of turning points of each polynomial. Okay, so let me see if I get my graphing calculator working. I think I got it working. I know I tried to use it last week. It kind of comes and goes. Let me finish. Let's finish my attendance for today. Yeah, I got to check on these students. Some of these guys I haven't seen for a while. Okay, let me see if I get this calculator. It should be working. Looking good. Let's reload and refresh. Cool, okay. So here's my virtual calculator, right? Not gonna show, oh, there it is. Let me hide this for now. And let's go here. Let's go, where am I? I'm working in QuickTime, now I'm gonna hide everything else. Cool. Okay, so we have this virtual calculator. All right, so in my y equals in the upper left, I'm going to put in x to the power of 4 minus 7x squared minus 18. Okay, I'm going to go ahead and put in the next one. We have this x to the power of 3 plus x squared minus 12x. Okay, and I'm going to go ahead and put in the third one, x to the power of 3 minus 3x squared. Did I hit the right minus? I did not hit the right minus. Minus 3x squared plus 3x minus 1. Now, so I can do each one individually. I'm going to scroll over to the equal sign, and I'm going to suppress the second two, right? So notice the first one is highlighted, the second two are suppressed. And then I want that window. So I'm going to go to window. The x's are already set, and we want y to go from -30 to 30. -30 to 30. I'm gonna do the y's by 3. So the y scale is by 3. Okay, I'm gonna hit graph. So for the first one, we're expecting a W. Okay. Notice that the leading coefficient is positive, so it goes up to the right. The degree of the polynomial is even, so the left side does the exact same. Now we didn't find the zeros. It says find the number of turning points. So the turning points you see, right? There's 1, 2, 3 turning points for that first one. Let's see if we see it here, right? There's a total of 3 turning points, 2 minimum and 1 max, right? So let's look at part B. I'm going to go ahead and suppress part A and engage part B. Now, if we're looking at B, the leading coefficient is positive, so that means the graph should go up to the right. The degree of the polynomial is odd, namely that 3, so it should go down to the left. We have at most 2 turning points, right? So it should go up to the right, down to the left. Now we can factor and find the zeros and find some more information, but for right now, oh man, that actually might be coming. Polynomials get a little intense because it's a lot of stuff we can talk about with that one concept. But at least it should be going up to the right, down to the left, and we have at most 2 turning points. Let's see what it looks like. Up to the right, down to the left, and we got our 2 turning points, right? So this one, we have our 2. And then let's just go back and go ahead and look at the third one. So now I'm going to suppress the second one and engage the third one really quickly. Leading coefficient is positive, so it should go up to the right. The degree of the polynomial is odd, it should go down to the left. It has a y-intercept of -1, and we don't have the information on the x-intercepts. We could find it, but we're just going to do this, all right? We said up to the right, down to the left, y-intercept is -1. No turning points, all right? Because it never went from increasing to decreasing. So it's increasing over the entire domain. Okay, we're almost there. We got about 10 slides remaining. So now we're asked to sketch the graph of this. Okay, let me give myself some space for this one. So I'm going to put this back, put that away. Let me get a copy. Okay. So now, let me let's do something here because this can be a little bit involved. Let me add another page. Let me change my view to seamless. Let me go paper, and I want some graph paper. Okay. All right, so we're asked to sketch the graph of this, right? So now, there are several steps. I'm trying to see what I can. The first thing that I usually like to do, first I want to find my intercepts. Intercepts, right? What else have we talked about? So we have some stuff there. We talked about multiplicity. That'll come out in the intercepts. We can do the leading term test. So we can say the leading term test. I'm going to say a few additional. There might be some more that come out, but I'm going to say a few additional points. Few additional points. And then let's graph after that. Okay, let's do this for now. We might add to this list, right? So let's start off with the intercepts. Now, with the intercepts, let me see. So we're working with f of x. Working with f of x equals -x cubed minus 4x squared plus 4x plus 16, right? So now with the intercepts, I would recommend start off with the y-intercept first. So let's start with the y-intercept. Okay. So to find the y-intercept, we set x equal to 0. Okay. So if we set x equal to 0, we're going to have f of x equals -x cubed minus 4x squared plus 4, that's not a 4, 4x plus 16, right? And again, we're doing when x is 0. Okay. So then, let's see. This first term goes to 0, the second term goes to 0, the third term goes to 0. Only thing we're left with is 16, right? So the y-intercept we get was 0, 16. Let me highlight it so we can use it later, right? Boom. So now after the y-intercept, let's go ahead and find, naturally, let's find the x-intercept. Okay, so to find the x-intercept, we set y equal to 0. So let me get a copy. Let me copy this and paste. We're going to set this equal to 0. All right, so then now we want to see, okay, can we factor this? So it's 4 more terms, so I'm a fan of factor by grouping. if I look at the first two, what can I factor out of the first two? I can factor out negative x squared, right? So then what's going to be left if I factor out negative x squared? X plus 4, right? So the hint is we're looking for another x plus 4 over here. What can we factor out of the 2 on the right to finish with that result is 4, right? So now there's a common binomial factor, namely both terms have that blue thing, so we can factor that blue thing out of both terms. So if we factor out the x plus 4, we're going to be left with, I'm going to write it as 4 minus x squared equals 0. Okay, hopefully this is okay. Okay, but we can factor further. We have that's difference of squares. It's a special factoring scenario, right? So the difference of squares, and again, this is I'm just bringing the x plus 4 down. So something squared minus something squared factors into 2 minus x and 2 plus x. Okay. So I don't think we have any multiplicity, like there's no higher power. So these all have a multiplicity of 1, which means that, so let me see. So the zeros that we get from the first one, we get what? X equals negative 4. We get x equals negative 2 and x equals 2, right? These all have an odd multiplicity. So let me just say the multiplicity is odd, or is 1, right? So what this means is that the graph is going to cross at these, right? So then I think we also said we can do the leading term test. So let's look at the leading term test for this. Shoot, let me undo that. Okay. So then let's look at the leading term test. Okay. Let me get a copy of this. Paste. Okay. So from the leading term test, the leading coefficient is -1, which is negative, which is less than 0. So that means our graph goes down to the right. Down to the right. So it's going to fall to the right. All right. The degree is 3, which is odd. So what that means is that the left does the opposite, so it goes up to the left. Okay. Let me highlight these intercepts. So we got our x-intercepts, y-intercepts. We know that it falls to the right, rises to the left. X-intercept, y-intercept. And then since the degree of the polynomial is 3, we have at most 2 turning points. Let's see, a few additional points. So you would list out basically the x-intercepts, and you would just want a few additional points between and beyond your x-intercepts, right? So we have this -4, -2, and 2. So like a few additional points, I would do something like, we can do like when x is -6. Let me say a few additional points. Let me clean it up. So just a few additional points. These are between and beyond your x-intercepts, okay? So like the far left, I might choose something like, I'm going to say when x is -6, I'm going to find the corresponding y. Let's see, let's do when x is -3. I just did halfway between the 4 and the 2. I think we already did when x is 0. So let's do -1 and 1. Let's do when x is -1, and let's do when x is 1. And let's also do when x is, I'm going to go 5. mean, 5 is fine. All right. So I just chose some points between and beyond. Let me move stuff down a little bit. Okay. We could actually use a calculator for this. I'm going to use a calculator. Let me pull it back up. Okay, I'm going to go to my y equals. I'm going to clear all this out. And I want to put in negative x cubed minus 4x squared plus 4x plus 16. Okay. So then what I'm going to do to calculate each of those, I'm going to go, so if you see the clear button, to the left of the clear button, it says VARS. I think that stands for variables. I'm going to click on that. I want to go to the right where it says Y variables. So I'm going to go to the right. I want to click on number 1 for function and then number 1 for Y1. So I'm calling on that function that I just typed in. So now I did an open parentheses. I'm saying when x is negative 6, what is the output? Right? So that's way off our graph, so we probably won't use that one. So we get this point, negative 6, and it's at 3688, right? Really, really positive, right? When x is negative 3. So I'm just going to hit second enter to recall that, and I'm going to change that to negative 3. We get 475. That one's kind of high too. When x is negative 1. So I'm going to just call that up again. When x is negative 1. Okay, 33. Okay, that's fine. When x is 1. So I'm going to just call that up again, remove my negative. So when x is 1, we get negative 1. And then I'm going to call that up again, and when x is 5, we get this really low number, negative 2109. Okay, oh, 5. Okay. So we did pretty much, so now I'm just trying to think of a proper window, right? X went from like negative 6 to like 5. And the y values, I mean, we can honestly capture those. They went all the way, let me see. We got x-intercepts, y-intercepts. When x was 0, we got 16. Let me see. All right, I'll go on the y-axis. I'll go to 4,000. Right, well, we can do it. Like it'll be a little bit weird, the window to capture these, but I think we can see what we need to see. Right. So the y value will go to like plus or minus 4,000, and then the x value we need to go to like plus or minus 7. Okay. So I'm gonna get rid of my calculator for right now. We'll bring it back up momentarily. So let's see. We said the y value, we want to go to 4,000. So let's just do 5, 10, 15, 20. No, I don't think we can get it to fit. Let me see. That might be a little bit ambitious. 1, 2, 3, 4. I wonder if we can get to 3. Let me see. 1, 2, 3, 4. I think we can get one more on either end. 5, 10, 15, 20, 25. Okay, we'll go by 500s there. And then we want this to get to what, 6? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. Okay. So this is the positive x in this direction. This is the positive y in this direction. All right. This is the origin. We said this was 1, 2, 3, 4, 5, 6, 7. This is 1, 2, 3, 4, 5, 6, 7. These were negative values. And we said we did the y-axis by 500, right? So we said this was 500. This is like 1,000. This was 1500, this was 2000, and this was 2500, right? This is again 500, 1000, 1500, 2000, 2500. Okay, and these are negative, right? Okay, so let's go back. So the first piece of information we have what? The y-intercept was 16, right? So 16, if that's 25, I mean, it's really, really close. It's basically like here. I'm going to just label it as 0, 16. And then the x-intercepts that we had, and again, these all had an odd multiplicity, so they should all cross. -4, -2, and 2. So then -4, -2, and 2. Okay. We said the graph should go down to the right and up to the left. So over here, it should be going like in this direction. Over here, it should be going in this direction. Okay. And then we just found a few additional points. Now that 6, I think, goes off of our chart. So we should be going off the graph before we get to 6. -3. Just let me see. I feel like that should be negative. Okay, let me go back and redo -3. I think I may have made a mistake there. Let me check. No, that's not supposed to be there. Right here. Can it show up if I slide it over like this? Well, here. Let me see if I can call up the -3. I feel like I made a mistake somewhere. Positive. Are we missing a 0? Oh, wait a minute. Up to the left, down to the right. Let me think about it. It should cross at the 2, so 1 should be positive. What am I doing wrong? Did I type the original thing in properly? Let me look at the original again. Maybe I typed it wrong. So here, let me pull up my calculator again. So I'm thinking I made a mistake somewhere. If I go to y equals -x cubed minus 4, oh, there it is right there. I don't even know how that happened. So plus 4x. All right. So right there, let's insert, we missed the plus, 4x plus 16. Okay. So we need to go back and adjust these numbers. Okay. So now, when I do y equals, if I do -6, 64. I was about to say, that's so much better. I was like, why are these numbers so outrageous? Okay, we'll make these adjustments. So I'll do these in red so we know that these are all adjustments. Okay. So for instance, when it's -6, we got a positive 64. Okay, that's so much better. At -3, we got -5. Okay, now we're cooking. -1, we're at 9. This is better. Then at +1, we're at 15. And then 5 should be fine. There's a -189. Okay, that's better. So I definitely made a keystroke error. We found the error. Let's go back and make these adjustments. So we need to adjust the y-axis. So let me get rid of these guys. And this. And I'll do my adjustments in red, like the things that I'm changing. Okay. Okay, so the y values, I mean, I guess if we choose something other than 5, we can get closer, right? If 2 is that one, let's just choose 3. So I'm going to change this from 5 to 3, just to have a more reasonable result. So then, when I choose, if I plug in 3, we get a negative 35. Okay, that makes the window just easier, negative 35. Okay, so now if we go to what, like 40, maybe 80, 20, 40, 60, 80, 100. Okay, so we'll go by 20s. So then I'm going to say 20, 40, 60, 80, 100. So 1, 2, 3, 4, 5. Yeah, that's fine. 20, 40, 60, that's not a 60. 60, 80, 100. Again, these are negative. Okay. And so that means we need to adjust this y value as well, this intercept. We could leave that though. Let's get rid of this. Okay. So now the y-intercept is 0, 16. If that's 10, so that's going to be about here. That's better. So now I think we did negative 6. There we go. Negative 6, we got our positive 64. So that's 70. And let me see, paper. Now for graphing, I actually do better with the dots. 60 is there. So 60, that's 70. So negative 6 should be here. All right, that's negative 664. Okay. Negative 3, negative 5. That's better. So that's 10. So negative 3, negative 5 is about here. Okay. Negative 1, 9. So that's about here. And then 1, 15 is like close to that one. And then 3, negative 35 is here. It's not negative 15. Negative 35. All right. So notice we have the features that we were looking for. So if we connect these points with a smooth curve, we get the following. Something like this, and it finishes the way that we want. Right? So we get a graph that looks something like this. Right? Okay. So that was an adventure. And then now we can actually compare that to this guy. So if we go to like window, let's see, we did the x-min, we can do negative 10 to 10 is fine. And then the y-min and max, we did negative 100 to 100. And we can go in steps of 20 to be similar to ours. So then if we hit the graph, we should get something similar. Right? That was an adventure. Okay, let's try another one. We're almost done. These last couple of ones do get a little intense, so you know. Let me go paper. Okay. And let me pull a screenshot. Do I want that or not? It's not. Well, I'm just going to add a copy of. Oops. Okay, let's try that again. I'm just going to add a copy of the calculator so you guys can reference it later. And let me get rid of this. And I can move this like about here. Okay. Okay. So we did it by hand. You saw what we did. I know it's a little intense. I mean, that's just the nature of it. This is why I encourage you to like link up with the tutors, because I know sometimes the way I do it is just intense. So hopefully someone else can say it a way that's more receptive, right? Where it's more simple. I say it as simply as I can, but some of this stuff just is not simple. There's no way around it. paper, actually. Let's go view, single page. Okay. So we did that one by hand. Looks pretty good. All right. So now what the book did, they said, first they did the leading term test, right? So the degree of the polynomial was 3 and the leading coefficient was negative. That negative leading coefficient means we go down to the right. Because we have an odd degree, the other side does the opposite. So they did that first. Then they found the zeros and their multiplicities. And so with those zeros and the odd multiplicity, they all cross the x-axis. They don't bounce, right? Then they found the y-intercept. I usually find the y-intercept before the x-intercept because the y-intercept oftentimes is easier, but you know. And then they found a few additional points. All right. So once they had the x-intercepts, they found a few additional points between and beyond the x-intercepts. Then they put all those together, and you get a graph like this. Okay, I think this is the last example. So we're actually express the volume of the wine barrel as a function of x, and it says assume these factors. Okay, so let me add a page. Let me change my view. Let me add one more page because I feel like I'm gonna need some space. Let me change the view to seamless. Okay. So express the volume of the wine barrel. So now volume is like you know, area, like for instance, the basic shapes here is basically a cylinder, right? So with this volume, all it is, if you take the basic shape of the base, which is a circle, the area of a circle is pi r squared. And then you're going to say that times the height, which is basically the length of the barrel. And that should get us there. It says assume that the height divided by the diameter equals the square root of 2. Okay? So again, the basic shape. So if we want the volume of the shape, we're basically going to say the area of the circle times the height of the barrel. All right? So let me do paper. So again, just in general, is my pen dying? Again, the area of a circle in general terms is pi r squared, right? So then if we want the volume of the cylinder, is going to be pi r squared times the height, right? Now we just need to update this for our image. Let's see. It says the diameter, we're given, I'll do that in blue. Let's see, it looks like the height of the barrel is what, 2z. It looks like the diameter, I'll just call it d, is going to be what, 2r. We want to get everything in terms of x, okay? So from here, and another piece of information we're given, we have what, this right triangle, where, again, this is like a 90-degree angle. Let's fix that. Okay, we are given that this is z, this is 2r, and this is x, right? So we want to get everything in terms of x. So again, in general, the volume of the cylinder is pi r squared h, but we can, let's see. So let's work with the diameter first. Okay. So we can use Pythagorean theorem, right? So if we have a right triangle with these properties, it should be the case that z squared plus 2r quantity squared should equal x squared, right? We're also given a piece of information that 2z divided by 2r equals z divided by r equals the square root of 2. Okay, let's see if we can put this together. Let me see. The height is 2z. Oh, so that's a relation. So let me see. Let me think about it for a moment. So we know that, for instance, z equals r times root 2. So let's just use that for now. So we have that z equals r times root 2, right? Can we get, so we got z in terms of r. Okay. Okay, so if we have z in terms of r, we can use this Pythagorean theorem. We can get that in terms of r. So let's plug that in for z. So then it should be the case that r times root 2 squared plus 2r quantity squared should equal x squared, right? I'm just trying to see if this helps us. So then let's keep going with this. So then we get the x squared equals 2r squared plus 4r squared, right? So then we get x squared equals 6r squared, right? Okay, so now we got x in terms of r, and the height is in terms of z. I feel like I'm getting a little bit recursive, but we can get the height in terms of z. I mean, height in terms of r. Okay. Let me think about it. Pi r squared, I haven't used that yet, right? 2z because we want to finish with x, right? We want the volume, let me see, r, we got r in terms of x, so we need h in terms of x. That's the only thing that we need because we have r in terms of x. You see it there. So the only other thing we need is h in terms of x. So what's the relation between z and x? So I think we used that already. Let me think about it. I'm trying not to look at the answer. So we just got to get everything in terms of one thing, right? So let me see. We got r in terms of x. We can get it from there. What about z in terms of x? Or the height in terms of x? So I might back up. I'm not gonna erase what I found. Um, can we get z in terms of x? Let's see, z over here. Well, the only thing that I see where z is like Pythagorean theorem, but I feel like I used it already, and so I feel like I'm being recursive as a function of x, right? For instance, if I wanted to get z in terms of x, is right there. Instead of solving, but I feel like that's going to make things worse. Z equals r. I mean, you could switch them. Okay, I'm gonna, just for the sake of like not droning on. Let me see. So the volume, we got that 2 pi r squared times the height. We got that. So then right there, right? Yeah, I started to do that. I was like, I was hesitant because it was going to be in the denominator. They got the x squared over r squared equals 6. So then they got it in terms of r. They got r in terms of x. Let me see. So we have r in terms of x. What's the height? 2z. So what if you write z in terms of r? Right there. z in terms of r is going to be r times the square root of 2. Okay, so let's work with this. I think I see it now. Pi r squared h. Before I go further, let me do it here. So the volume pi r squared h, right? But then the h is 2z. So I'm going to say pi r squared times 2z, right? But then we already have z in terms of r, so let's go ahead and make that switch. So then this is going to be pi r squared times 2r root 2, right? I just plugged in for z. I switched out the z for the r root 2, right? So then if we shift things around, we'll get 2 pi root 2 times what? R cubed, right? So that's the volume in terms of r. Am I being recursive if I do that? Because I have, so now if x equals 6r squared, so from here, let me do this in a different color. From here, I'm going to solve for r. Divide both sides, let me divide both sides by 6, so then we get r squared equals x squared over 6, and then take the square root on both sides. Normally it's plus or minus, but for the context, we're just going to take the positive. So then r equals, it should be like the absolute value of x. If you take the square root on both sides, x over root 6. I'm going to leave it like that, right? So then, let me see if this works. So then ultimately the volume in terms of x is going to be 2 pi root 2 times x over square root of 6 quantity cubed. And you can kind of simplify that down. You're going to have what, 6 root 6? So x cubed over 6 root 6. Okay, let me see. I mean, we can, let's try to simplify this down some. So this is the same as 2 pi root 2 x cubed. On bottom, you got root 6 times root 6 times root 6. So that's going to be 6 times the square root of 6. 6 times the square root of 6. Okay. This turns this into a 3. And if we rationalize, like top and bottom by the square root of 6, we're going to finish with something like square root of 12 x cubed over 18. We can take it a little bit further because 12 is what, 4 times 3? So then that's going to be 2 pi root 3 x cubed over 18. And then I think the final thing, we're going to see what happens. Pi times the square root of 3 x cubed over 9. That's as far as I could take it. I'm not confident in that. Let's see what they do. Okay. So volume, 2 pi r squared times the height. Now let me think about that. Did I do z or 2z? I did 2z. Pi r squared, the height, it should be 2z, right? Let me see, did it have a 2 in there? Yeah. Pi r squared times the height, right? So that's where that 2 is coming from. So then we also have that z over r equals the square root of 2 and Pythagorean theorem. So we had those 3 things that we were trying to condense down in one. That's why I was a little bit back and forth, right? So they gave us, this is like the volume of a cylinder. This was just additional piece of information they gave us. And then this was the Pythagorean theorem, right? Okay. So then from here, let me see. If you divide everything by r squared, I'm not really sure why you would do that, but you can get x squared over r squared equals this because the r is gone there. And then this one, right? Now z squared over r squared is 2, right? Because if you square both sides, that's where this 2 comes from. So then x squared over r squared equals 6. And we had got to that point, right? We had x squared over r squared equals 6, right? So then we got r squared in terms of x. Take the square root on both sides. R equals x over root x. Now I saw this and then I hesitated because I was like, well, I didn't want to have to deal with like fractions, so I was avoiding it. But we eventually had to come there, so that's why I went on there. So now we got r in terms of x, but the only thing was the height, right? So now we got r equals x over root 6, and then z equals 2r, root 2 times r. So then now they got z in terms of x. So z equals x over root 3. So then they basically put all the pieces together. Pi over 3 root 3 times x cubed. Let me see, I think that's what we got. 3 root 3. If we leave that in the denominator, yeah, we get the same thing. Times x cubed. Man, that was an adventure. Okay, so I mean, it does work out like that sometimes. You know, that's just the nature of the beast. I can't think of a more simple way to do that. Oh, I think if we had done like a system of equations, but that's a whole nother thing. We're not there yet. You know, as those pop up, we can just sit down and talk about them and work through them. I know that one was a bit rough. I felt like if we were doing it like in matrix styles, like that might be a little bit easier. But, you know, it was really just trying to get everything in terms of one variable. You know, so we get r in terms of x, we got z in terms of r, and then they took those two and put it into the original equation. Well, okay, so that was an adventure. So we're going to end it there. And we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.